before discussing the exercise, why don't we look at one example to see how they execute, how they find the stationary point, and how they later use Hessian function to determine the nature of the stationary point. Okay, so let's look at this function. Okay, please note that every function that you see will have their own graph. Right, later we're going to see how does this the graph of this function look like. Okay, and we're going also to see whether this stationary point determined in this solution is true. Right, so first, before we can determine use Hessian function to determine the nature of our stationary point, of course we'll first need to look for a stationary point. So to look for a stationary point, in other words, to look at the point where the slope equal to 0, in other words, there is no slope, the line will be horizontal, right? To do that is by conducting, right, by calculating the first partial derivative and later make it equal to 0. Why should we do that? Remember that the sole purpose of conducting differentiation is to finding the function of a slope. Right? So when you conduct the first derivative here, it will give you the function that later will calculate for the slope at certain point. So if you say this function equal to 0, meaning we want to say that this function has no slope, or slope equal to 0. That is what we want, right? Stationary point, slope equal to 0. The same goes for the partial of y. We are going to find the first partial and later we are going to put it equal to 0 for the same reason. Okay, now that we have these two functions, right, function 1 and function 2, we are going to figure out the stationary point. So just take one of the function. Okay, for this solution, they take the first function, and from this first function they come up with 2x, right? So the first one x equal to 0 and the second one x equal to negative 2y. Now the next thing to do after you have x is to find, of course, the y. So it's this solution substitute x equal to 2y into another equation, which is equation 2 here. So every variable that contain that is x will be substituted to negative 2y, and this is what the solution gave us. So solve for it, and you got y equal to 0, y 1 over 2, and y equal to 1. So we have 3y here. So the same goes for another one. We have x2, right? x0. So substitute x0 also into the same equation, doesn't matter. We get y equal to 0. So now we have a pair when x0, y0. When x negative 2y, meaning that when you put negative 2y and 1 over 2 here, you need to substitute also y 1 over 2 into the equation, right? Let us write it down. Just now we have a stationary point for when x0 y0, and we also have when y is negative when x is negative 2y right? Y will be either 1/2, or another one, it can also be, right, we put -2y 1, right? We have, when you input x equal to -2y, this is what you get, 1/2 and 1. You also get 0, but 0 is equal to this one, so it's overlap, we don't need to write it down. So now, this is still not the coordinate, we'll need to substitute them accordingly. For example, we need to substitute, to obtain x, we need to substitute y1/2 into the y, into this y, y1 into this y. So basically, the stationary point is actually equal to 0, 0 for the first one, and then we have negative 1 with 1/2 for the second one, and -2 and 1 for the third stationary point. So basically, this solution tells us that the function that we calculate just now have 3 stationary point, or 3 area that consists of slope equal to 0 or no slope. Okay, let's see whether it is true or not. So this is the function for the previous example that we are looking at, right? If you try to draw it in the graph, this is how it should look like. So the point that we find just now, 0, 0, -2, 1/2, and -1, 1/2, -2, 1, and -1, 1/2, right? So we have 0 here, 0, 0. So you can see it stay on there. If you try to zoom in, you're going to see that actually it is on the flat area, or slope equal to 0. How about the second one, -1, 1/2? Okay, it pointing out here. So we have area that is slope equal to 0 there. Also for this one. So this is the 3 area that being pointed out in our solution, right? These 3 area. So this is, if we have this graph, we are able to know that, okay, so this graph at this point is at this area, so this is how the slope look like after that, and for this one, this is how the slope look like, and then after for this one, this is how the slope look like. So that is if we have the graph. What if we don't have a graph? How do we determine the nature of this point? Right, we're going to use Hessian function. Okay, so for Hessian function, now that we have these three stationary points, we will use this function. So actually, the component in Hessian function is not that complex, because they just want us to multiply between two partial second derivative, and then subtract with the mixed partial derivative squared. So I believe that you have already know how to look for these components, right? So just after we have the stationary points, just proceed to look for the second partial derivative and mixed partial derivative. Alright, you can look for either one, whether it is x and y or y to x, right? Because they are the same. After you have all of the information, right, all of this component, okay, test one by one. So first you input all of this component in the Hessian, so you'll get this, and then just substitute the stationary point one by one. For example, for point 0, 0, when they input 0 in x and y in the function, they get Hessian equal to 0. So When Hessian equal to 0, it means that there is no conclusion. Okay, no conclusion. So next they input the next point, which is negative 1 over 2. So they input it accordingly in the function, and they obtain negative 6. Negative 6 is less than 0. So whenever your Hessian is negative, right, that conclude that that point is on a saddle point. What is saddle point? Saddle point is a point where, let's say if your graph is moving downward, right, let's say it is moving downward, and then you'll meet the stationary point, so basically the minimum point, right, where it lay flat, and then after that stationary point it continue to go downward. Alright, so that point is known as saddle point because it continue to turning down, going down, right? So that is saddle point. Alright, so next we have negative 2, 1, substitute in the equation, and it get 24. So 24 is more than 0. So whenever the Hessian is positive, more than 0, right, you cannot really actually conclude it yet. You'll need to look at the second derivative. So then substitute with the same x and y. So for this one, it get negative 6 and negative 28. Both of them is less than 0. So in a situation where Hessian is positive 24, and the second derivative is negative, less than 0, we can conclude that that point show a maximum point. What is a maximum point? Maximum point is a point that you can imagine it from a graph that is going upward, and then until you reach a maximum point, the highest point. After that it goes down. So this so we can also say that this maximum point is a turning point. Just to compare with saddle point, maximum point or minimum point is known as a turning point, because when the graph, for maximum point, when the graph goes up, meet with that point and later it turning down, that is known as a maximum point, a turning point. The same goes if later, if you calculate for Hessian, it is positive, but then you look at the second derivative, it is also positive for both of them. So we can conclude that this is a minimum point. If you to imagine it, just imagine a downward graph meeting with the stationary point there, and then go back upward. So the turning point from downward turning to upward. So that is for the minimum point. As for a saddle point, it is not a turning point, right? We can call it an inflection point actually, but that is the other terms for it. So saddle point, if it goes downward, it meet with the point, stationary point, so it goes horizontally, and then after that it continue to move downward, that indicates saddle point. The same goes if the graph is from below going up and then meeting with the saddle point, which is flat, and after that continue to go upward, that is a saddle point. Otherwise we know it as a turning point that can be maximum or minimum point. So we can imagine this point without really need to draw a graph. Okay, so that is on how to use Hessian. So basically we first need to find the the stationary point by using the first partial derivative, and then we proceed to look for Hessian to find the nature of this stationary point by using the second derivative. Okay, so that's it for this video. In the next video we are going to discuss on the exercise. Okay, so thank you.